In classical deductive logic, a consistent theory is one that does not contain a contradiction. The lack of contradiction can be defined in either semantic or syntactic terms. The semantic definition states that a theory is consistent if and only if it has a model, i.e., there exists an interpretation under which all formulas in the theory are true. This is the sense used in traditional Aristotelian logic, although in contemporary mathematical logic the term satisfiable is used instead. The syntactic definition states that a theory is consistent if and only if there is no formula P such that both P and its negation are provable from the axioms of the theory under its associated deductive system. If these semantic and syntactic definitions are equivalent for any theory formulated using a particular deductive logic, the logic is called complete. The completeness of the sentential calculus was proved by Paul Bernays in 1918 and Emil Post in 1921, while the completeness of predicate calculus was proved by Kurt Gödel in 1930, and consistency proofs for arithmetics restricted with respect to the induction axiom schema were proved by Ackermann, von Neumann and Herbrand. Stronger logics, such as second-order logic, are not complete. A consistency proof is a mathematical proof that a particular theory is consistent. The early development of mathematical proof theory was driven by the desire to provide finitary consistency proofs for all of mathematics as part of Hilbert's program. Hilbert's program was strongly impacted by incompleteness theorems, which showed that sufficiently strong proof theories cannot prove their own consistency. Although consistency can be proved by means of model theory, it is often done in a purely syntactical way, without any need to reference a model of the logic. The cut elimination implies the consistency of the calculus. Since there is obviously no cut-free proof of falsity, there is no contradiction in general. Consistency and completeness in arithmetic and set theory. In theories of arithmetic, such as Peano arithmetic, there is an intricate relationship between the consistency of the theory and its completeness. A theory is complete if, for every formula phi in its language, at least one of phi or phi is a logical consequence of the theory. Presburger arithmetic is an axiom system for the natural numbers under addition. It is both consistent and complete. Gödel's incompleteness theorems show that any sufficiently strong effective theory of arithmetic cannot be both complete and consistent. Gödel's theorem applies to the theories of Peano arithmetic and primitive recursive arithmetic, but not to Presburger arithmetic. Moreover, Gödel's second incompleteness theorem shows that the consistency of sufficiently strong effective theories of arithmetic can be tested in a particular way. Such a theory is consistent if and only if it does not prove a particular sentence, called the Gödel sentence of the theory, which is a formalized statement of the claim that the theory is indeed consistent. Thus the consistency of a sufficiently strong, effective, consistent theory of arithmetic can never be proven in that system itself. The same result is true for effective theories that can describe a strong enough fragment of arithmetic, including set theories such as Zermelo-Fraenkel set theory. These set theories cannot prove their own Gödel sentences, provided that they are consistent, which is generally believed. Because consistency of ZF is not provable in ZF, the weaker notion relative consistency is interesting in set theory. If T is a theory and A is an additional axiom, T plus A is said to be consistent relative to T if it can be proved that if T is consistent then T plus A is consistent. If both A and A are consistent with T, then A is said to be independent of T. First-order logic. Notation in the following context of mathematical logic means provable from. That is, a B reads, B is provable from A. See list of logic symbols. In other cases, the turnstile symbol may stand to mean infers, derived from. See list of mathematical symbols. Definition: a set of formulas in first-order logic is consistent if and only if there is no formula such that an otherwise is inconsistent and is written inc. is said to be simply consistent if and only if for no formula of both, and the negation of a theorem's if is said to be absolutely consistent or post-consistent if and only if at least one formula of is not a theorem of, is said to be maximally consistent if and only if for every formula, if con, and are well defined. This falls out of the fact that is an equivalence relation and also requires a proof that and are independent of the choice of class representatives. Finally, can be verified by induction on formulas.